Hello and welcome to section 2.6 related rates, and we've got a few examples. And please remember that if you have any questions on any of this stuff, please ask in class and anything that we do in the video, so always be asking questions. So we're going to start with this problem, and we're going to say we're going to go through and say that x and y are both differentiable functions of t, and they are related to the given equation. And so we're going to find some information. So just like when we were doing implicit differentiation, we were going through and differentiating y's in terms of x's. Now we're going to differentiate everything in terms of t in this equation, because that's what they're telling me to do. So I'm going to go through and differentiate y, and when I differentiate y, it becomes 1. But since I'm doing it in terms of t, I'm going to call it dy dt. And so then that equals, well, when I differentiate x, that becomes 2x, just like I would before. Following my power rule, I get dx dt. And then finally the 3 is a constant, so that just becomes 0, and so I don't really need that, but that's really what we're talking about. So now if I go ahead and basically they want me to find what dy dt is right here, and so I already really have that equal to 2x plus dx dt. Then I just kind of go through and pick apart what they gave me. So find dy dt when x is 1 and when given that dx dt is 2. So that basically means that dy dt is going to equal 2 times 1, there's my x, and then dx dt is 2, and so if I just multiply those together, I end up with 4. And so that's just a basic related rate. It's nothing, it's just getting you used to the new notation. So our next example, we're talking about ripples in a pond, and we're going to have to kind of think about this, and this is where it gets a little bit of a challenge. The pebbles being dropped into the pond, and concentric circles, the radius of the outer is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, what is the total area that is disturbed by the water changing? So we should probably write down the stuff that we know. And so let's see, we know that, that the outer ripple is increasing at 1 foot per second. So the key is when you hear 1 foot per second, that is a measurement per time. So that's going to be like dr dt will equal 1 foot per second. We know that. We want to know the specific is when the radius, what is happening, what is the rate, what is the how is the area changing. So we want to know what dA dt is. That's what we want to know for the specific case when r is 4. So this is our specific case that we're going to deal with. And then the other thing is, what do these circles look, or what does this shape look like? Well, they look like circles. So the other thing that we know is that the area of a circle is found by pi r squared. So that what we're going to deal with when we're dealing with these guys is we're going to have to come up with an equation, something like pi r squared, and then we're going to have to differentiate it and basically go through and plug in what we know. Now, don't plug in stuff too early. Remember that, well, just know that if we plug in stuff too early, things are going to disappear, and that's not what we want to have happen. So we're going to differentiate this function in terms of time. So when I differentiate a, it would become 1, and so we're going to call it dA dt. So the area is changing with respect to time. And pi, remember, is a constant, so it's just a constant multiple, so it's going to stay there. And then when I differentiate my radius, I get 2r, but I want it in terms of time, so dr dt is what I get. So there's my equation that I'm dealing with. I want to know what dA dt is. That's good. I'm already equal to it. When my radius is 4 and my dr dt is 1. So I can go ahead and just plug in my information, my know stuff. And so dA dt will be pi times 2 times 4, which is my radius, and then times my dr dt, which is 1. So when this is all said and done, it's changing at 8 pi feet per second, and that's how the area is changing per second in this one. So in the next one, this time we have a spherical balloon, and the things that we're looking at, let's see, it says the rate of 4.5 cubic feet per minute, and find the rate of change of the find the rate of change, so that's a good piece of information. Find the rate of change of the radius when a radius is 2 feet. Okay, so the know stuff. What do we know? We know that we're dealing with a volume of a sphere. So we need to know the equation of the volume of a sphere, and I believe that is 4/3 pi r cubed. That's something we know. We're dealing with a volume. We know that dv dt is changing at dv dt, when they're saying the rate of the volume is changing at 4.5 cubic feet per second. We know that. We want to find, and so now what we're trying to find is how is the radius changing. So dr dt is what we're looking for, and in the specific case the radius is 2. So this is our specific case. This is what we're looking for. This is how the thing is changing in general. Well, good news is for this one is everything's in terms of r or v, so we only really have two variables. We already know what dv dt is. We're looking for dr dt, so when we differentiate this, it's not gonna, we don't have to do a whole lot. So I'm going to go ahead and differentiate this. So dv dt is going to equal 4/3 pi, because that's my constant, and then my radius turns into 3r squared dr dt. And so now, as I do this with a little bit of simplification, well, the 3's will cancel out, so it looks like that I will end up with dv dt equaling 4 pi r squared dr dt. And if I want to move these guys around, I have to divide by 4 pi r squared, so it really becomes 1 over 4 pi r squared dv dt will equal dr dt. So basically I just had to isolate the term that I was looking for, dr dt, because that's what my question's all about. And so I'm going to differentiate. Now that I've differentiated, I can go ahead and plug in. And so I've got 1 over 4 pi. My radius, that is my specific case, is 2 squared, and then dv dt is, I could write it as 9 over 2, which might make it a little bit easier for me, and that'll equal dr dt. I mean, that's 4.5 still, so I just wrote it like that. So with a little bit of simplification here, 16, looks like I get 9 over 32 pi is really what I'm looking for. And for how my radius is changing with respect to time, and you could get that as a number, and it would be approximately 0.09 feet per minute is really how the radius is changing with respect to time. So remember, if you have any questions on these, please ask in class. So let's try the next one here. So this time we have a plane flying overhead, and we need to figure out how it is, what its altitude is, or basically figure out how it's changing. So if s is decreasing at a rate of 400 miles per hour when s is 10, so we're going to go through and figure out what will happen as the plane flies directly over the radar station. So a couple things we need to know is the fact that the stuff that's given to us. So we're given that we know, let's go through our know, and we know that s is decreasing at a rate of 400 miles per hour. So ds dt is going to be negative 400 miles per hour. We also know that's when s is 10. So when s is 10, we know that. We need to find dx dt, that's what they want to know, when s is 10, and so that's what we're trying to find, and we need to find out what x will be. Well, if s was 10, then we could go through the Pythagorean theorem and say, well, x squared plus 6 squared will equal s squared, and so x squared will equal s squared minus 6 squared. And since they want to know exactly when s is 10, we can say x squared equals 100 minus 36, which means that x squared has to be 64, and so x has to be 8. So also the other key piece of information is that x has to be 8. So this is our specific information. This is the stuff we know. And so then the question is, how are we going to deal with this? Well, our equation is back to the specific, because you notice it's a right triangle over here. So we'll go back to our general equation and we'll say that s squared is going to equal x squared plus 6 squared. And this is general for any plane that's flying 6 miles above the ground and how it's approaching the radar station horizontally and on the diagonal. So we're not using the specific case yet. So I'm going to go through and differentiate this, and when I differentiate this, I get ds dt times 2s will equal 2x times dx dt, and the 6 squared is just 0 because it's a constant. It's 36, and 36 differentiation of 36 is 0. So I'm basically looking at something like this. Remember that we want to know what dx dt is. So if I divide by 2x, 2s over 2x times ds dt will equal my dx dt. So now I have all this information right here that I can plug in and find out how it's changing as we approach the radar station. So I can cancel out the 2's. So I've got s is 10, x is 8, ds dt is negative 400, and that equals dx dt. So with all my simplification, I'm going to find out that dx dt is going to be negative 500 miles per hour when I simplify that. And basically what that means is, well, the question is, if it's speed, it's 500 miles an hour. So that means that's the rate at the plane is changing as it's approaching the radar station. It's going at 500 miles an hour. And so the speed is 500. And remember that speed is just the absolute value of the velocity. Velocity has direction, speed does not. Speed doesn't matter whether you're going forward or backwards at whatever miles per hour. It's just how fast you're going. So then finally we have this last example, and we're looking at how the angle of this is changing, how the angle of the camera is changing as the space shuttle, which is no longer around, takes off. So we're filming it, and we have this position function that is given to us of s equals 50t. So the stuff that we know for this one is that we know our function is s equals 50t squared. We also know that if you're looking at this, let's see, well, we can find ds dt. If we could find ds dt from this equation, if we differentiate it, we would end up with 100t, because if I differentiate this in terms of t, I don't have to do a dt over dt. That seems silly, so it's just ds dt. We also know that if we're trying, well, let's go through it. They want to know that the change of the angle. So they want to know d theta dt over time when the time is specifically 10 seconds. Time is 10 seconds. Or, yeah. And so that's what they want to know when it's specific to that. And so then we also need to figure out, you know, how high off the ground it is, and that would be my s value, which is over here. You can see my little s value. So that's, we also need to know the height. And so the height after 10 seconds, if I plug that in, would end up being s will equal 50 times 10 squared, which would be 5,000. So we needed that to also help us out. Whoops. We need that to help us out to find out how the angle is changing. Well, for this angle, and we could use any trig function since we're dealing with this, but the trig function that we're going to use is tangent, because we have the opposite. We could find the opposite, and we know the adjacent, so that's probably our best bet. So we're going to say the tangent of theta is going to equal the opposite, which is our unknown height, over our adjacent, which is our distance across the ground. And so then we get to go ahead and differentiate this in terms of time. And so when I differentiate this, remember that this is a chain rule. So I differentiate the outside, which becomes secant squared theta, and then I multiply by the inside, differentiation of theta is d theta dt. And then over here, well, the 2000 is just a constant multiple, so I could write that as 1 over 2000. And then when I differentiate s, it just turns into ds over dt. And so knowing some things here, let's see, okay, we're trying to find d theta dt by itself, so we are going to divide by secant squared, d theta dt. And remember that secant squared, or secant itself, secant of theta is really 1 over cosine of theta. And so when I divide by secant squared theta, it basically is flipping the fraction over. So I really have 1 over 2000 cosine squared of theta ds dt. So now that I have that all the way I want it, I can go ahead and plug in my information that I know. And so I know that for d theta dt, that's going to be equal, well, ds dt we just said was is 100t, so I could write this as 100t over 2000 times the cosine squared of theta. All right, well, that kind of helps. But as I do this, I have to think of what cosine is in relationship to this triangle. Well, in this triangle, remember that I have that cosine would be adjacent over hypotenuse. And so my hypotenuse in this case is going to be, well, if I do Pythagorean theorem, it's going to be 2000 squared plus s squared will equal the hypotenuse squared. And so this hypotenuse is really the square root of 2000 squared plus s squared. And so if I'm going to use cosine squared of theta, I'm going to say d theta dt equals 100t over 2000. And then cosine is going to turn into the adjacent, which is 2000, over the hypotenuse, which is what I just calculated, of that triangle. All of that squared. Which then, if I plug in my given information, I know what t is. I know t is 10. I know that s in this specific case is 5000. So if I put all of this into my final equation here, I have d theta dt to equal 100 times 10 over 2000 times 2000 over the square root of 2000 squared plus 5000 squared, all of that squared. And so with a lot of number crunching and all of that stuff, we can go ahead and find out that the rate of change is 2/29 radians per second. And again, remember, if you have questions on this stuff, please ask in class, but this is the basic setup of how we're going to go through these things. You're going to do your know and what you need to know, and then you're just going to figure out what the function is that you need to solve for. So this is we will do a lot more in class, but please ask questions if you have any. Thank you.